Hello and welcome. My name is Terrence Barkin. I'm the Executive Director of the Graphene Council, and we're extremely pleased to host Cardea today to talk about graphene biosensors. Presenting on behalf of Cardea is Dr. Brett Goldsmith. So Brett, we're really looking forward to hearing about your technology. Tell us what you have.
Thanks, Terrence. It's great to be here. I'm really happy to be presenting for the Graphene Council. So yeah, I'm going to be talking about graphene electronics and biosensors and a little bit about how and why standards matter. And I am the CTO and co-founder of Cardea. So Cardea makes graphene-based biosensors, and we're typically out there talking to people in the wider biosensor community. So this is just a diagram of what the sensor looks like. This is what a picture of one of our chips. And then you've got the design, and then it's a transistor liquid-based sensor. And there's a lot of material out there about that. One of the things that's kind of interesting as a graphene scientist is that the wider biosensor community doesn't really appreciate or recognize what's being done with nanomaterials. And really part of that is because in nanotechnology, and I didn't realize this until really deep into commercialization, nanotechnology, we typically work on what is part of a biosensor system. And that plays into this conversation about standards as well. But as a nanotechnologist, for me at Cardea, it's really rewarding when I see customers use our systems and take the lead in applications like gene editing optimization, beating out the legacy optical tools that we're trying to show graphene has the potential to the ability to outperform. So this presentation is a bit on kind of how we invented this technology and how we developed our own internal standards to get there. One thing I should say is when I started in this field, we were already standing on the shoulders of folks who had been doing integration of transistors with biology for decades. And it's probably we're talking about this for a minute. It's 20 years ago or so. I was electrically measuring lysozyme and enzyme, interacting with biomolecule via carbon nanotube transistor, very related to graphene. And then every time I did a measurement, I got something different. And at one point, the biochemist I was talking to mentioned that each individual lysozyme molecule I was measuring was slightly different. Proteins and biology in general is just a lot more varied than you might expect. Every single molecule has a slight customization. A bit of extra sugar there, a tweak in an amino acid here. And that's not mutations. That's because biology is created by a set of really messy room temperature processes. 20 years ago, we were seeing signs that carbon-based electronics was going to succeed where integrating biology and electronics with existing semiconductors failed. This diagram of this transistor here, you can draw it with a silicon transistor. It won't work. It will with graphene. So at that time, 20 years ago, no one had the technical understanding or the expertise necessary to create a scalable system or concept of what that would look like. Just getting the biochemistry right, just these antibodies bound to the graphene, just getting that right was a PhD. And there was a PhD to make the graphene, and there was a PhD to design the chip, and another PhD to fab the chip, and so on. So getting a scalable system concept together took a lot of time, working out and coordinating many projects. And that's what needed to be worked on, and that's what we've done at Cardea. So we use this word often outside the graphene community. We'll talk about what we do as a biosignal processing unit, or a BPU. Now, as long as the marketing folks aren't listening, right? What this really is a GFET, a graphene FET centered electronic biosensor system, and what we're trying to do is emphasize the difference from kind of legacy biosensors. So what our platform is it's everything you actually need to use an electronic biosensor based on graphene, from the reader to the chemistry to the software. You can see this whole list of things here. This is just some of the modules that go into the whole system. And it's all packaged together in a customizable system because the biologists are always wanting to change this, what we call here this wetware layer. So, a lot of folks in this community, the graphene community, have been asking how do we do this. And we've shared what we know works when we can. We've published some papers, and we've tried to be careful not to talk about just lucky results. And so to kind of work these things out, we had to develop standards and designs for each one of these components, and actually more components than this. This is just a kind of diagram. But we had to make sure that we could validate what we were doing and that we weren't hurting our long-term business and IP when we shared. But today we can share a lot more, which is great. And it's exciting to see that as we've gone along and we've developed and invented processes, these now get incorporated into a lot of academic work. And now it's time to kind of take the next step and go from just, hey, here's a couple of things that work, and really start raising the quality bar as a community and saying, this is what we need to do together as material producers, application developers, system integrators to make something function for our end customers who are outside our field. And I just want to be clear, like in case anyone's wondering about what I'm talking about, what I'm saying is that we are open to business for anyone who wants to talk to us about using any of this and learning from us about what we're doing or developing their own applications. So kind of now that introduction to Cardea is done, part of what I'm talking to you about today is how we as a graphene community can improve quality, improve reproducibility, and kind of how standards play in that. And that leads us to the ISO Technical Committee 229. And this is, I would say, 2022. Has been a year of kind of maturation of the conversation regarding the industry and graphene standards. The Graphene Council played a huge role in that with the graphene classification framework. And so we at Cardea, we also wanted to get on this committee. And when we got there and we started seeing the framework coming through for approval as an international standard, Terrence and I had a couple conversations about how it was going through the editing process, because there was one thing that was very important to me that's missing from here, which is electronics grade monolayer CVD graphene. And so that began a conversation about well, what should the standards be around monolayer CVD graphene? How do you do electronics with graphene, and how should that be approached from a standardization point of view? So not all of us may be familiar with the kind of high-level workflow for graphene electronics fabrication. And so I've summarized the whole process to 5 steps here. It's really kind of hundreds of processes, maybe close to about 1,000 steps now is what we use. But you can kind of bin them into five groups here. Starting with metallization and going through to your burn-in testing at the end. Graphene started off as an electronic material. The famous paper won the Nobel Prize was about the electronic properties of graphene. And I think that the future is really still there as well, still in the electronics world. When I was starting, we were still doing Scotch tape, and we needed to go from that to something that was scalable. And we had just had access to CVD graphene back in those days when Cardea was starting, and we really wanted to get into commercial fab. So what we found was that there were a lot of processes that didn't exist or needed to be drastically changed. And the first step here, this wafer metallization, that's basically standard electronics, graphene growth and transfer. A lot of us know how that works. The material producers are really upping their game there, and that's where a lot of the standards are coming in. But then you've got how do you do the next few steps, the lithography and the passivation. If you want to, what we found is if you want to do any sort of scaled electronics manufacturing, you've got to figure out how to do hard mask. You got to figure out how to passivate your chips, and that's a little bit different with graphene than with other electronic materials. So we had to invent a lot of processes here that are now standardized. Dicing and packaging is the most expensive aspect of electronics manufacture. Same with graphene. Interestingly, it's not the graphene that's most expensive. It's the dicing and packaging that is. And then the burn-in, I think this is something that a lot of people forget about, but this is standard in electronics. And, we want to customize this for graphene, but the final testing, you want to test your chip in a realistic environment before you release it. And so figuring out how to do that is very important. There's a few footnotes here. My business folks here have nicely requested that I just remind everyone some of the patents that we've got in this area. Moving on into, then what does some of these things look like? I'm going to start with something that's really, I hope, should be obvious to all of us, right? So all of us in the graphene community can look at this and say, okay, this is a place we all agree we can start. There's some obvious QA and standards issues to be identified, right? So if you're growing graphene on a metal foil, most commonly it's on copper, and then you go to use it, if there's wrinkles or, God forbid, folds or oxidation, those are quality failures. Those that's going to impact your product. What you really want to do is when you receive the material, or when you're growing it yourself, when it gets out of the oven, you pull it out, and then again, right before you're going to look at it, you want to be able to look at the graphene on copper and say, is it wrinkled? Is it oxidized? This is easy technically, right? This is a very easy thing to do. I remember when I was doing this, with academic groups, just getting the students to do this on a small piece of copper reliably was often difficult. So now we have to do this on dozens of very large sheets of copper every week, and that can be very laborious. The answer is you want to automate absolutely as much as you can, and that's what we do. We automate tons of stuff. So it takes, quality control, and using standards takes time, attention to detail, discipline, documentation, and a lot of patience. It's easy to just say, well, we can do Raman and AFM and look at what the graphene looks like, but really just sitting down and carefully looking at your material by eye is going to save you a lot of trouble down the line, particularly if you don't have access to automated systems. Moving on to something a little more complicated, but this is still something I think a lot of us have seen. I try to make these images as clear as possible. Hopefully you can see. This top image, this is what we're looking for. We've transferred the graphene onto the wafers. We need to check how things went before moving on to the next stage. Remember, that packaging stage is the most expensive. So what we want is at least 90% of the transistor channels to have no observable defects near the channel in the graphene. Following kind of the Pareto principle, 80% of the defects come from 20% of the causes. So PMMA residue and graphene tears are the primary issues with PMMA-based transfer of graphene. If you look at this bottom image, you'll see the tearing that I'm talking about here, just little tiny holes in the graphene.
And we found that using an automated microscope that has a trainable AI to detect these is really helpful. It requires running through a lot of wafers, but if your problem is trying to do QA on a lot of wafers, then needing to run a lot of wafers on an AI training algorithm is not an issue. But this is kind of the next bar in graphene quality. It's how the graphene flows into the next step of the process. I'm going to skip over some of the more standard electronics quality checks and then go into this burn-in testing, because I don't think that this is something that I see out there a lot, and I think this is where things get really interesting. Because if you don't do burn-in testing, you don't really know how the variations in your feedstock material, such as your graphene, or kind of small, quote, insignificant changes in your process are affecting your final product. So again, because graphene material standards are still being written, this burn-in testing is something we do on every chip, right? We've got a lot of internal standards. We still do this on every chip. We do this before we release to the customer, before we release to internal R&D. Everything gets tested. And once again, a ton of automation. You can see in the foreground, there is a stack of chips in kind of the packaging we use to move them around manufacturing. And then there's this line of automated liquid handlers. We make BPUs. So our burn-in test is running a short automated assay in some biological buffers. I think, kind of digging in a little bit deeper on this, one of the things that you really want to have on hand when you're doing electronic testing of graphene, when you want to say like, hey, is my graphene device working right? You need to have a device model. And if you think about what the silicon folks do, they absolutely have models of how their devices should work. We should do the same. And this is unfortunately an area where the academic literature has really let us down as a community. So to me, the best model out there, other than ours, is a piecewise model out of MIT. But you just don't want to use a piecewise model for this kind of thing. I am a physicist, and so this is my opportunity and my required one equation per talk here. So you see, I've got my equation up here, if you'll indulge me for a bit. This is a summary of our device model, and you can see it's fit to some data there for a transfer curve. This is different. If you followed the Cardea publications, this is a bit of a different model from what we published maybe 3 or 4 years ago. And there are some really interesting features. Probably the first thing that some of you might notice is that the carrier mobility, it doesn't appear here. And we do have a term that's unfortunately non-physical labeled skew here. And that term is not where you might expect it. It's not out of the square root where you might expect the mobility to be, but it's associated with the capacitance. And we've found that the capacitance is probably the area that's most driving skew in terms of n-type and p-type transconductance slope. So we put that term there. This is, we're not here to go into this, but the point is, after a couple of decades of transistors being used for biosensing, it's surprising when we see still people just kind of, put some goop on a chip and see a change and then say, here's a change without understanding what might drive it. Buffers or preservatives or biology will influence different factors in your model in different ways. And, you should put a little bit of thought into physically what is possible. And your test should reflect that. Part of this is handing to a biologist a chip where they need to have this level of understanding in order to understand what to attribute a buffer change or a salt change or a contaminant from a biological interaction. The biologists aren't equipped to do this. We're equipped to do this on the device physics side. So we really need to do that. And this has been, I think, for a long time, a source of some credibility issues with us in the graphene community, with the biology community, biosensor community as a whole. Something we really work on. So zooming back out, I guess, to the chip manufacturing practicalities. If you've got a good model and you've got a good test, and you've made this feedback loop where you have an internal test you can run, you understand how to judge your material coming in, how it's being applied to the wafer, the resulting performance in a test assay, then you can develop something like this, a nice tight distribution of key parameter. This is direct point in a particular buffer. And this is a batch of 20,000 chips. Doing something like this is critical because it shows me as a device manufacturer that all the other steps, all the other QA I've done has been correct, that I can at the end get something that is understandable, and I can attribute changes to this to changes in the process or changes in the material. Having good quality control, having good standards accelerates this process and this feedback mechanism. So that's hugely important. Understanding also an application that comes out of this, like what is the right thing to track, having that, then the next level, and I think you'll hear from Kiana in a little bit about this, our CSO, on what this does on the assay side. It kind of gets to the next level of how do you evaluate if you're looking at the right things from a standards and a QA point of view. Remember back at the start when I talked about all the proteins being different. If all the proteins that we're looking at are a little bit different, we want to know how to characterize the variation in the biology separate from the variation in the graphene and the variation in the manufacturing process. So it all needs to be quantified. Okay, so like the next level, right? How do customers use a chip? You want to have something where the person who's going to sit down and use what you're producing doesn't have to understand the device physics, doesn't have to understand electronics or software. They can just use it. So that's where the whole system point of view comes in, that how the system works around the graphene is in many ways as important as how the graphene itself works. And so we automate once again, and you'll see it's the same liquid handlers we use for our test assay, and that's because it's great to reuse technology. This video is sped up, but it shows how the liquid handler is applying liquid to the chip. So we got 16 chips here, and by doing it this way, we ensure that the proper order of steps is taken, that there's no weirdness when the biologist is trying to pipette onto a graphene sensor the first time or anything like that. So everything just works better, and it kind of continues this concept of predictability, understanding variation that we started with just looking at the copper with the graphene. You remember this slide with all these things. I almost never show this slide because really this is what we show people, right? So we boil everything down. We take responsibility for all the little pieces that go into the whole system, and we say, okay, we're gonna just deliver to you an interface with fluid that goes in, and then software driven information out. And that kind of approach of understanding the interfaces and simplifying things down, taking responsibility for the complexity on our end so our customers can focus on the complexity on their end is our philosophy of how to make this work. To conclude, I guess the point is, even when you're thinking about standards, and particularly, standards for monolayer electronic grade graphene are hard because it depends on how you use it. So a whole system is required to really understand, is the graphene fit right for the application? And we can't evaluate graphene material quality until we get all the way through assay execution. So there really has to be a lot of conversation, a lot of back and forth with the material providers, and there has to be a lot of understanding of the whole system. Graphene has really great properties as biosensor. I mean, it's going to change the world, how we interact with biology as human beings. But making it work reliably is much harder than I think a lot of us understood in the beginning. Standards are important for that. What the Graphene Council is doing is important for that. What we've developed at Cardea and is in use out there is important for that. Hence this presentation. You'll see our CSO, Dr. Kiana Ron, show you some of the use cases for what we do, how our attention to detail on the manufacturing side has led to reproducibility and scale on the biology side. Now, if you are interested in talking to us about any of this, reach out to our VP of Partnerships, Dr. Francie Barron. She's the best person to talk to about how to work with Cardea. Thanks.
You had an interesting section in there on how the customer actually uses the chip, and I found that quite interesting because the technology that you explained, I think, is extremely useful to understand what underlies it. The level of quality control that you have and the normalization on the signals and that kind of benchmarking are obviously very important, so people can trust that the outputs that they get and how to read those. But the question I have is, who is the actual customer for Cardea for this versus the end user? And what I'm thinking of is you have diagnostics companies that maybe are making tools, and I'm going to wrap another question in there as well. Is the customer purchasing the chip and then they're putting it into a device and then they get the software, so they're doing the reading all on their site, or is this a service you guys provide? So there's two questions in there.
Yeah, it's sometimes difficult to separate service from product, right? And particularly with the stage of development that the technology is in right now. Part of the reason we've seen rapid adoption of a lot of the techniques we've been talking about for the last few years in academia is it's easy to take a rack of electronics from a physics lab where I learned and hook up a device. And there's a lot of smart people out there that can read the papers and figure out how to write their own software and apply their own voltages. But the customer for Cardea is not actually those academic groups. It's the medical device companies, the system integrators that are going to be using the technology for their own application. So we don't foresee ourselves making a lot of fully featured, fully complete systems that go to the actual end user. That said, we expect our end user to be at the most strict level, a doctor or a patient, and trying to diagnose something. And so that sets a really high quality bar that we try and meet, because we'd like to see this get all the way through to that point. And in the beginning here, those big companies, the medical device companies, they don't know how to use the technology. They don't know how to write software for graphene, analysis of graphene sensor data. They don't know how to do the analog front end that drives our chip. It's not that they can't, it's that we have to have a demonstration system to show them, and then that allows us to move into, okay, how do we take this piece and integrate it with your system?
Got it. I think there are a lot of parallels in other adoption curves for different graphene technologies, because if you think of it, one is understanding the material. graphene in itself, how it's produced, how it can be manipulated, and also what it's capable of doing, right? Which you guys obviously have mastered. You've taken it the next step with the integration, putting it into a chip that you can just quality control, turn over to a device company. But now we come up against the how much do they understand what it is? How much do they understand what it's capable of doing? How can they exploit that? Right. So
Yeah.
there's a bit of that customer education. Can you talk to me a little bit about? There's two themes I want to kind of pull on here and extract out of this. Graphene is a material, we're talking about it because it can enable us to either do things we could not do before, or it can enable us to do things we are able to do, but it can do it much faster, more accurately, to a higher degree of sensitivity. Talk a little bit about what graphene does to extend the boundaries in this field of diagnostics.
Yeah. Yeah, it's a great subject. I could talk for another half hour on that. So the primary thing that graphene does, kind of from a physics point of view, taking it from the kind of fundamentals up, is it's a semiconducting material that, or at least we'll say a field sensitive material that is not chemically reactive with salt water. So if you take silicon and you put it just, the silicon channel, and you put it in salt water, it oxidizes right away. And that's true of almost any other electronic material that's field sensitive, but graphene is fine. And so it allows us to directly integrate electronics in the environment of biology. What that does for the end users, for the not just the device makers, but also the doctors and patients, is it gives higher sensitivity, higher speed to the biochemical reactions happening. And sensitivity in this context doesn't necessarily mean analytical sensitivity, and that's commonly misunderstood. Analytical sensitivity, like how low concentration can we measure, that's going to be set by the biology. Sensitivity in this context means what kinds of biological interactions can we measure? We can measure all of them. And that is unique. There's no other technology, there's no other material out there that you can say, yeah, it can measure nucleic acid hybridization, it can measure antibody antigen, it can measure a small molecule interaction, it can measure an enzyme, anything. And so graphene allows us to do that. The word that is often used in the biology space right now is multi-omics. And actually, if you look at Cardea's website, we talk about multi-omics all the time. Multi-omics is the way I see it, the experimental or the laboratory embodiment of systems biology. Systems biology is the idea that you can't understand biology just by looking at genomics or proteomics or any of the omics is. You look at the whole system. Multi-omics is the idea that you can't understand what biology is doing from a measurement point of view unless you also look at it from a genomics, proteomics, small molecule metabolomics point of view simultaneously. Well, graphene lets that happen.
So as a layperson, when I hear this, what I understand is I have the opportunity now potentially as a diagnostics company or as a biosensing company to use one platform and the same kind of infrastructure, but I can target all sorts of molecules and proteins and systems without having to change my hardware, but I can use the same platform. Is that a fair assessment?
That's right. Yeah, exactly. That's correct. So with a graphene-based system, you can change what you're looking at by changing small elements of the biology, right? So when we put our BPU diagram up there, what we say is you change the wetware, you change the antibody out, you put it on an enzyme, you put on something else, and then you change the analysis, which is the software side. But the things that are traditionally the cost drivers and the things that you're working around from a medical point of view, kind of the big tools, the hardware, those stay the same. Now, because it's small and it's electronics and it's nano, the hardware is also tiny and it's low power. And there's all these great features that come with it. I don't think the medical world is ready yet. And certainly the regulatory world, it's not ready yet for us to push all that far in one go. But, one day we're going to be walking around with handheld devices that can tell us not only, is there a genetic marker around that might indicate something, but also protein markers, environmental markers, small molecules, all that kind of stuff. And it's going to be based on graphene.
Well, that is very exciting when you think of, from my personal history, I've dealt with many medical societies in the past, and if you look at the recent pandemics, the topic of community health, where you have pervasive monitoring of a society in a positive sense, where you're able to detect early on pathogens that maybe are introduced before they get out of control, that would require some really sophisticated sensing equipment that is inexpensive and low cost to operate and low power, but it could save society untold, death, harm, and money.
Yeah.
By being an early warning system or an early detection system. So that part of what this enables is really quite exciting. Now, one of the issues we've seen with adoption in all industries is many of the legacy players who have substantial presence in a market are not always the most open to innovation and change, for obvious reasons. But one thing you said really caught my ear, and that is that many of these diagnostics companies may not have the capabilities necessarily to do the software part of this, right? So you have the sensing platform, you have a hardware for the interpretation or harvesting the signal, and then you have a software component. And please correct me if I get any of this wrong, but the software component is then to correctly interpret the signals that you've obtained for whatever the particular biology is that you're trying to detect. I was kind of shocked because I would imagine that a lot of these companies do have internal capabilities for a lot of this for their own devices. What is this device competing with against primarily? Is it a different type of technology platform? Is it ingrained systems? Is it a lack of even awareness or skepticism about using carbon in these environments? What is the biggest adoption obstacle, either technical or human behavior or assumptions?
Yeah, that's a good question. I think that there's a couple of big adoption hurdles. There are some technical adoption hurdles. The medical world is built around optical assays, and everything from the buffers used to the disposables that go along with all of diagnostics are optimized around optical assays. And so we find we have to adapt to that and correct for it at times. And that can be a big challenge, because something that doesn't matter to an optical assay matters a lot to an electronic assay. That's something that's manageable, at least for me as a scientist. That's okay. The human aspect of things is a bit harder. So there's a lot of people that are happy with the way things are. Medical field moves really slowly. I think I heard as the other day that it takes more than 10 years once there's a new medical standard set for that medical standard to be adopted widely. And that's after the standard is set. So it's a very conservative field. And so when you say, look, we're going to replace for this assay an ELISA that's been around since the 1970s, folks say, well, why? And that's where the pandemic actually played a big role in helping to answer why. Well, sometimes the legacy technologies aren't sufficient to the challenges that we face today. And when you're looking around and saying, gee, sure would be nice if we had, the technology available to prevent future pandemics. That means, you've got to improve the core technology that you're working on sometimes. So, ELISA might not be the best thing to base all of our medical diagnostics on.
Understood. In this question, I don't know if this is appropriate or if you want to address this or not, but what we've, again, to see in the adoption curve, if you're just making graphene, I'll use this as an extreme example. If you were just making graphene and sending, a copper coated sheet of this to a diagnostic company and say, hey, you should really use this, it's fantastic, then obviously they have to do everything from that way up. And what my question is getting at is, you've already, as a company, Cardea has already gone vertical integration quite a bit in putting this on a platter, basically. Here's the chip. We've run these quality controls. We've run the software so that you can calibrate it, and it's pretty far along. Do you see the need to go even further in vertical integration to get to adoption, to remove more obstacles, or what does that look like? How much do you have to do for a customer
Yeah.
to address some of those, maybe sticking points?
That's a great question. Yeah. So does Cardea or does the graphene community need to have more vertical integration to actually get to the point where we're leaders in some of these markets in the diagnostics or monitoring space, right?
Yeah,
And
that was put better than I asked it. That's
right. I don't think it's necessary. However, it might be helpful, right? And so this is something I've talked to some folks in the graphene community about. We often in the graphene community look around at each other and we compete. A lot of us are competitive people, but we're not competing with ourselves. We're competing with other folks who have other technologies, and some of them are really good, and other emerging technologies, some of them really good, and we can do better. And so where vertical integration could help is in directing more energy towards cooperation. So that's where it's not necessary, but it could be helpful.
Well, I appreciate the sentiment that you raise, and you'll know that we echo that, right? As the Graphene Council, we feel that graphene has certainly matured, especially in the last just few years. It's really matured quite rapidly, and we are not really competing with one another. There are so many applications where graphene can be applied, and even within narrow applications, there's so much territory to be plowed, so to say, that no one company is ever going to do all that on their own. And we really do need to collaborate together in a positive sense. And we're competing with legacy technology, right? In most cases. So definitely agree with that sentiment and would echo that. And on the standard side, I do want to shout out and give kudos that, you've been a huge help in us understanding the needs for this particular type of graphene material. For those who maybe are not that familiar with graphene, it's not one material. It's kind of like a family of materials with different types and forms, each of which are engineered to perform a different task, because graphene has these superior properties of extremely high electrical conductivity, thermal conductivity, transparency in a single layer, et cetera, et cetera. So it's really important to get the right graphene for the job. And then within that, what we see with this presentation with Cardea is to go a step further and to target what graphene can do with its amazing properties to solve really significant, meaningful problems. And I can't think of many areas that are more meaningful than human health and addressing, diagnostic is the front end of fixing whatever's wrong with us.
Yeah.
And what comes down the pike.
I'd like to echo a little bit of what you just said and say that I've been super impressed as I've been able to work on the standard side with Graphene Council. The overall message that I'm trying to say of, look all the way through your application, get all the way to the end user before you think that you understand your input material. I know the other folks who have contributed to the standards that the Graphene Council is putting out are thinking that way. And so it's really great to see us as an industry, mature like this and really take this, end product focused point of view on what we're doing. And so it's a bit more complicated maybe with a biosensor, and particularly when you start saying, and it's going to be used for medicine. But the philosophy is the same.
Well, I'll say it again. This is a really, really important area for medical advancement. Treatment is obviously where a lot of attention is positioned, but detection and accurate diagnostics, reliable diagnostics, more sensitive diagnostics, a wider array of biology that can be detected is absolutely critical to also know where to point the therapeutics at. And so if there's anybody there who's interested in developing applications that leverage and take advantage of the capabilities of this technology, then we encourage you to get in touch with Cardea. And if you want any information about graphene in general, the Graphene Council is a neutral global trade body. We are agnostic when it comes to graphene suppliers. We work with suppliers, end users, intermediaries. We also interface directly with regulatory agencies. And our sole mission is to help educate people how to use graphene materials to improve whatever products or industry sectors you might be active in. And so we're very proud to have Cardea as a member of the Graphene Council and having contributed to this community. And so, Brett, I want to thank you for your time and appreciate working with you.
All right. Thank you, Terrence.
All right. Good luck. Take care.
Bye.